Okay, in this example, we're told that we have air approaching a normal shock. So let's sketch this out. Here's our normal shock. We have some air approaching it. And we're told what the temperature is there. So we're given T1, P1, and the velocity there. Let's go ahead and write those out. Notice the pressure is an absolute pressure. The temperature, however, is not an absolute temperature, so it's worthwhile for us to convert that over. So let's see, we'd add 273 to that. So 273 added to 18. Sorry, I have to do that. It's 291 Kelvin, right? Okay, so we have the conditions upstream of the shock wave, and we're told the temperature immediately downstream from the shock. T2 is 551 Kelvin. So you see the temperature has gone up quite a bit across the shock. We're asked to determine the velocity immediately downstream of the shock, the pressure change across the shock, and to calculate the corresponding pressure change for frictionless, shockless deceleration between the same speeds. If it's frictionless and shockless, that means it'll be isentropic. So we're going to find what the isentropic pressure change is for part 3. So let's do part 1 first. Find the velocity immediately downstream of the shock. Well, we're given information about the temperature upstream and downstream. So I know from the first law analysis, if you go back through your notes on the first law analysis for compressible flows, it's one of the first things we did for compressible flow. I know that there's a relationship between the temperature and velocity, and it looks like this. Let me just write it out, and then I'll explain it. So that's the expression. This is for an adiabatic flow. Basically, what this is the stagnation temperature here. It's related to the stagnation temperature, but this is it's Cp times the stagnation temperature. Let me just write that here. That's what I'm trying to say. But what it's saying is that the specific heat at constant pressure times the temperature plus the specific kinetic energy remains constant. This was something we derived in the lecture for an adiabatic flow, so I'm just applying it here across the shock wave. The shock wave is actually an adiabatic process. You can go back through the notes and take a look at the derivation for that, but it's adiabatic across there, so the stagnation temperature remains a constant across the shock. So the conditions upstream and the conditions downstream for the stagnation temperature remain the same. We're given the information about T1 and T2 as well as V1, so we can solve for V2. So I'll underline the things that we know. We know the specific heat at constant pressure. We can look that up for air at that given temperature. So and we're going to assume that that's a perfect gas so that the specific heat at constant pressure remains a constant. As long as the temperature change is smaller than a few hundred Kelvin, then that's not an unreasonable assumption. It'd be more accurate if we didn't make the perfect gas assumption and allowed the Cp to vary, but we're not going to do that here. We're just doing a simple calculation, so we're going to assume the Cp remains constant. The velocity we're given as well, and the temperature downstream is given. So we can solve for the velocity downstream, and when we do that, that comes out to be 254.3 meters per second. So the key to solving this first part for the velocity downstream of the shock is just to recognize that the flow across the shock wave is adiabatic, so the stagnation temperature remains constant, and that stagnation temperature is related to the static temperature and the velocity in this manner. You could also, of course, find the Mach number and use the Mach number stagnation temperature ratio expression. It'll get you the same result, but it just takes a little longer to get there. This is a more direct way. Okay, now for the second part, we're asked to find the pressure change across the shock. So what I'm looking for there specifically is the delta P, which would just be P2 minus P1. So that's what I'm working toward. Since with compressible flows, we often deal with ratios, I'm just going to write this as a ratio, where I have P1 times the ratio P2 over P1 minus 1. It's just easy because there's an expression for the change in the pressures across the shock wave, that pressure ratio P2 over P1, we have that expression in the normal shock relations. Let me go ahead and write that out for you. The derivation's described in the notes, and this formula is on the formula sheet. So let me just go ahead and copy it down. Okay, so that's the expression. So we can plug in our upstream Mach number. Now we have to find what the upstream Mach number is. The way we find that is, since we have the velocity upstream and the temperature upstream, we can find the Mach number upstream. So let me work that out over here. So Mach number upstream would just be V1 over the speed of sound upstream. Speed of sound upstream for an ideal gas is just kRT1, where K is our specific heat ratio, and that's 1.4 for air, and R is the gas constant. For air, it's 287 joules per kilogram Kelvin. And then T1 needs to be an absolute temperature, so we do it in terms of Kelvin. And then when we work this out, we'll get the Mach number 1. Comes out to be 2.24. It's supersonic, as we'd expect, since there's a normal shock, the incoming flow has to be supersonic. So we can take that Mach number upstream, plug it into here, and that'll give us P2 over P1, so let's do that. P2 over P1 comes out to be 5.6880. You can either use this formula, which is totally fine, or you can use the normal shock tables. If you look at the very back of your formula sheet, you'll see some normal shock tables, and if you look up the P2 over P1 ratio for a Mach number close to 2.24, you'll see it comes out to this. You'd have to get this exact number, you'd have to do some interpolation, because the normal shock relations don't go to this kind of resolution. Anyway, now that we have the P2 over P1 relation, we can plug that in up here. We know P1, that was given right up here. So then we can solve for delta P. By the way, one thing I'll just highlight is, as you can see, the static pressure increases across the shock. Here it goes up by a factor of just over 5.5. So a pretty significant increase in pressure. So anyway, if we plug in these numbers, you'll get that the delta P comes out to be 4.73 times 10 to the 5th. Something's wrong here. No, this is right. 10 to the 5th pascals. Sorry. I looked at the wrong number. But anyway, that's how much the pressure changes across that shock wave. That's the delta P. So a big change in pressure. This is the ratio of how the pressure changes, and this is the actual delta P. Okay, so that gives us part 2. Now part 3 is calculate the corresponding pressure change for frictionless, shockless deceleration. This basically just means look at it for isentropic conditions between the same speeds. So we're going to do this between the same speeds here. So to do that, what we're going to do is we're going to do the delta P the same way, P1 times P2 over P1 minus 1. So this is going to be our isentropic analysis, where the P2 over P1, since the flow is isentropic, we're going to use the isentropic stagnation pressure ratio. So this will look like the following. Okay, so we have that expression. So these are just the isentropic stagnation pressure ratios. The P naughts will be the same because it's all isentropic, so it's the same stagnation pressure. And then in the numerator, we can replace that with a corresponding Mach number expression for the isentropic relations. Okay, so we have that expression. So we know the Mach number upstream, so we just solve for that over here. What we're missing now is the Mach number downstream, so we still have that to figure out. The way that we can find that Mach number is we can since we have the temperature downstream and the velocity downstream, we can go ahead and use that to find the Mach number downstream. So Mach number 2 is V2 over speed of sound 2, which is V2 over the square root of KR T2. And so we'll get then the Mach number 2 comes out to be 0.54. Now keep in mind that the problem specifically is asking what's the corresponding pressure change if we go between the same speeds. So what I'm assuming is that we're going from this V1 at 766 meters per second to this V2, but we're doing it isentropically. Okay, and so we're gonna use the same temperature and the same velocity here as our ending condition for this isentropic case. Okay, just so we can make a comparison. So we can go ahead and use that Mach number. And by the way, you can get this Mach number different ways, but this is the way we did it here. And then you can substitute it in, and you'll get that P2 over P1 comes out to be 9.3253, and then the delta P ultimately comes out to be 8.41 times 10 to the 5th pascals. So that's what it would be if you went between the same two speeds isentropically. Okay, I think that that covers everything in this example. This last part of the problem is a little bit tricky. You just have to keep in mind that we're trying to go from the same speeds. I should probably have written in here to make it clearer that we're also assuming the same temperature change. Okay, rather than going through the shock, we're assuming that we're going isentropically from this temperature to that temperature and from this speed to that speed. That probably would have been a better way to write this. Maybe I should have written same speeds and same static temps, just to make it absolutely clear. All right, I think that does everything for this example, so we'll end it there.